Hello. So today I'm going to be talking about our continued introduction to information security, but we're going to be focusing on the defense side, and particularly looking at what operating system security does. My name is Tyler Moore, and this is from the University of Tulsa. So here's an outline of the overall plan. We'll talk about threat models and what those mean. Access control systems for operating system security, and in the next video we'll talk about cryptography. So as a recap from last time, we talked about the difference between safety and security, and then we defined the three fundamental information security protection goals: confidentiality, integrity, and availability. And these were discussed, and we're going to be talking more about them today. So here is sort of a graphical overview of the process. So we have the protection goals of confidentiality, integrity, and availability, and we must then engineer defenses to satisfy those goals. So you can think of this as a digital analog to building a castle to protect your confidentiality, integrity, and availability of your data or whatever resources you're protecting. But in the meantime, there are attackers out there who pose threats to the security of these goals. To continue the castle analogy, we have attackers who develop a battering ram to try to breach the defenses of the castle. But then this process continues, where the defender can actually adapt and engineer new defenses to counter the security threats in particular. So finally, pushing this metaphor to breaking point, you could push down the portcullis to block the battering ram. So that's the overall sort of way to think about information security. Today we're talking about the defenses we're going to engineer. So, as I said, engineering defenses. Now, in order to decide how you're going to build your defense, you first need to think formally about the threat you're facing. So threat modeling is what is traditionally used in the computer science literature for that. So it comes from a recognition that all security is relative. You're not going to get absolute security. But the question is, what's it relative to? And so threat models are good to codify and make clear what the adversary behavior is assumed to be. And it does that in a couple of ways. First, it helps articulate the goal for the attacker, which could vary. For example, it could be to disrupt the defender's protection goals, or just to disrupt the confidentiality of the defender. It could be something at a higher level, like just to make money. And so and making money means disrupting the integrity of a system, then so be it. And then there's even approaches just to try to cause mass panic. So these goals really vary, and they can vary how you think about them. Then there is knowledge. So what knowledge do you ascribe to the attacker? Does the attacker know the architecture for the system he's trying to penetrate, or does he have to infer that? And then finally, we have capabilities. So typically we think of the computational power that's available to the attacker, the time that's available to target defenders, and for the case of cryptography, we often think about whether an eavesdropper who's trying to observe communications, whether that eavesdropper can do this locally, like on a single channel, versus a global eavesdropping adversary, like an intelligence service that can observe all network communications. And then finally, another distinction and capability is an active versus passive adversary. And a passive adversary would tend to just observe communications, whereas an active one, in addition, can actually directly manipulate the communications that take place. So, that's a quick tour through what a threat model is. And so a question to maybe help you think through this would be, could a threat model be fully specified by assuming a certain level of financial resources available to the adversary? So could we just say the threat model is an attacker who has a budget of $1 million? We'll discuss this more in class. Okay, so moving on to access control. So one of the claims made in the first introduction to security was that the authorization decision, deciding whether a user is authorized to take an action, is the fundamental challenge of security engineering. So if you get that right, you have a secure system. If you get that wrong, then you can't achieve your security goals. And so given that, it sort of stands to reason that you'd want to know what are the mechanisms that enable the authorization decision to be supported. And so and the way it's done in operating systems traditionally is through something called access control. And what access control is it ensures that authorized users can access and modify only the resources to which he's entitled. Okay, so an access control mechanism overlaid onto a file system, for example, would say that these files can be read or written by a particular user. But it's not just files; it's also processes. And when we think about how things work in operating systems, you have these separate processes that are very powerful that run the operating system key functions. Okay, so if you think about what an operating system needs to do, it needs to do some really powerful stuff. It needs to read all the communications and write to output devices. It needs to install software. It needs to overwrite key data, and so it has a lot of powers that are assigned to the operating system. And so the natural problem could arise is that if a malicious actor were able to develop software that uses these capabilities that are assigned to the operating system, then bad things could happen. So you don't want to allow any piece of software to be able to install other random software, because that would allow them to, say, install a keystroke logger that would observe communications. And so the solution to this has been traditionally for an operating system to create a superuser that can have operating system level capabilities, and then you constrain what a normal user can do. So you create this dichotomy of normal users who can run programs and maybe write to certain files, but that's distinct from a super user who can install software, can make changes to the operating system code base, can read low-level communications, and so forth. So given this distinction, the question is, how do you implement it? And so most operating systems tend to have a kernel, which is the central code base in the operating system that implements these sensitive functions. And then you can sort of visualize this by thinking that there are distinct processes, different programs that are running, and different operating system services that run. So these processes would then interact with certain resources like data files and input-output devices. And the way operating systems often worked historically is that these processes can then directly access other processes and also directly access resources. Okay, and so this is the way it was done in early versions of Windows, and the way it still is done to this day for many simple embedded systems and devices that we're seeing in the Internet of Things, for example. And so the problem with this is that it becomes very difficult, if not impossible, to regulate what a given process can do. So let's say you want to restrict process P2 from doing operating system level activities. Well, if he can directly access other resources, it's much harder to enforce that. So the solution has been to instead erect these virtual barriers between processes and resources, and instead require all communications that need to access other processes and resources to be mediated through the kernel. So these barriers prevent side channels and indirect communication between the processes, and it also ensures that only authorized processes can access resources when they have been allowed to do so. So this greatly improves the security of operating systems if you have a design like this. And this same principle extends not just to operating systems, but to virtual machines, which are widely used now. So a virtual machine is running on a resident operating system, but there are barriers that prevent any communication from that virtual machine instance back to the host operating system. So that's a high-level tour through operating system security. We will talk about one last component, which is the principle of least privilege. So this is sort of a design strategy that is used in order to try to mitigate the risk of information security threats. So what the principle of least privilege is, it states that any file or process should be assigned to the minimum level of permissions needed in order to complete a required task. Okay, so what this is basically saying is that you will give a process or a file access to all the resources it needs to get its job done, but no more than that. So you would only grant access to a resource if it is absolutely necessary. And the advantage of designing your systems and writing programs that adhere to this is that it can limit the damage that a process can cause to others, either inadvertently or if it's been taken over by a malicious actor. But the principle of least privilege has some downsides in that it often conflicts with the desire to make systems easy to use and adaptable. And computer scientists do tend to prefer to make a general system that would work in cases that we wouldn't even have possibly imagined. And so there's a tension between writing a general program and giving it access to only the resources that it needs to do a particular task. So there is sort of a long-standing tension between this sort of very nice ideal principle and how it gets implemented in reality. And so you can sort of think about this by thinking of what are the incentive conflicts that programmers face whenever they request privileges. So a programmer wants to get his task completed. He wants to make this work and make it work as seamlessly as possible. And he may only have a sort of a passing interest in whether or not the actual task itself is secure. And the last thing I'll end you with here is this screenshot here. So this is a screenshot from Microsoft Windows Vista. So this was the first attempt by Microsoft to really implement and support the principle of least privilege in the design of the operating system. So what it does is it created a warning anytime a arbitrary software program decided that it needed to access privileged resources, so that the user had to actually approve it. And so it sort of brought the user into the loop into deciding whether or not the particular resource needed to be granted access to. And in principle, seems like a great idea. In practice, it was a bit of a disaster for Microsoft because the programmers who were writing programs kind of weren't prepared for this, and they ended up requesting high levels of access to resources that they really didn't need, which caused these warning messages to pop up, whereas previously they didn't. So it sort of made apparent the over requests of privileges that software designers had been using. Okay, so that's going to wrap up our discussion for today, and we'll continue in the next video by discussing cryptography.